Good morning, everybody. Let's get started. So you should have received your midterm scores by now. So now you have a sense of the kinds of exams that you'll get in this class. So next week, Tuesday, if I'm not mistaken, is the next one, the second midterm. Very similar setup, similar number of questions, a few short answer questions. So hopefully you'll do well. So today we'll talk about problem solving, the psychology of problem solving. So here's a puzzle from a book. I think the book is called Amazing Mazes. I thought mazes were just for kids, but there are some mazes in there that are quite hard. And this is sort of medium hard, I think. So in this maze, you can only take, you start over here. You can only take right turns at first. At some point, you'll make your way over to the left side. And you can't just enter or reach its goal state by entering, by making right turns. So this little squiggle here turns your right turns into left turns only. And if you hit it again, you turn from left turn only to right turns only. And at some point, you'll have to reach your goal state over here. Has anybody managed to, in the few minutes that you've been looking at this problem, maybe you saw the slides earlier, does anybody have a solution? Not yet? All right, well, I'll let you think about it for a while. There's an interesting moment where you have to reach some sort of insight, like you're not getting anywhere, and you have to do something kind of different, kind of special. That's unusual for normal mazes, but it's a trick that works for this particular maze. So I'll come back to this maybe the next lecture, so I'll give you an opportunity to work on this. So today we'll talk about these topics. First, we'll go into well-defined problems, basically games, situations where everything is well-defined, rules are well-defined, the initial state, goal state is well-defined, and the kinds of heuristics that you could apply to solve these problems. Then we'll move to, I think what are more interesting problems, ill-defined problems, where there's some aspect of the problem that's not quite clear. And these are the problems where most people get stuck. And we'll talk about different ways to get stuck, having a mental set and functional fixedness. And then we'll talk about the psychology of insight. Can we tell if insight is used during problem solving? And what are the behavioral markers for insight? And then we'll end with expert problem solving. What makes an expert an expert? How is somebody able to reach like world level performance in some knowledge domain or even something like sports? What's the role of practice versus talent? So first there's this major distinction between well-defined problems and ill-defined problems. So well-defined problems have an initial state that's well-defined, so you know where you start. You know where you should end up. Like some goal state. And the key is that you're given all the rules of the game, so to speak, right? So most games, board games, there are well-defined problems. And AI researchers, so artificial intelligence researchers, they believe that by coming up with algorithms to solve board games, we could also perhaps understand how human problem solving works. So maybe we should compare computer programs that solve a game of chess or try to play a game of chess as best as possible to humans playing a game of chess. And maybe we get some insights into human problem solving. Well, we'll discuss how these well-defined problems require search through some space, the space of all possibilities. And because these spaces are large, you need heuristics to navigate these spaces in an efficient way. Now, ill-defined problems, there's some aspects that's not quite defined very well. So either you don't know where you're starting in with a problem. You don't know maybe what even the goal is, or you might not realize you have reached a goal. But in most situations, an ill-defined problem is a problem where you don't know what the rules are. You don't know what allowable moves are, and you don't know how you're supposed to even think about the problem in the first place. And some psychologists have proposed that in order to solve ill-defined problems, you have to think about it in a different way. You have to see the problem differently. Often, you might have to think about a suitable representation. And we'll give some examples where you have to sort of break out of a mindset of looking at the problem in one way, think about it in a completely different way, and that allows you to solve the problem. That is the key to the puzzle, to rethink the whole problem. So first, talking about well-defined problems. So a classic example of a well-defined problem is a maze, right? So you have some place where you start, some place where you have to end up, and you have some very simple rules of navigating through a series of obstacles. And so it's very clear what you can or cannot do to solve the maze. Another game that has been studied, so most games, by the way, are well-defined problems. All the board games that you can think of, chess, checkers, backgammon, those are well-defined problems. So here's a little puzzle that has been studied by psychologists, the Tower of Hanoi. So let's play this game. Interesting. Did I? Let's look at this link. All right, so the game is to move these disks, these 3 disks, from this tower to this tower, tower 3. And the rule is that you can never place a larger disk on top of a smaller disk. And so you have to get this large disk as the first disk over here, then the medium-sized disk, and then the smallest disk, in that order on tower 3. And you can move only 1 disk at a time. So tell me, from which tower should I move to what other tower? From 1 to 3, okay, and then? And then? Right. Okay, so then you solve it in 7 moves. And in fact, that's the smallest number of moves you can take. Now, let's see, let's restart this again. So one thing that's not easy to see is that it's better to move this disk to tower 3 as opposed to the middle tower. Now some of you see that, but that requires a bit of advanced insight. In fact, if you start over here, it takes at least 11 moves or so before you can recover from this bad initial move. So with an example like this, there's a search space involved. There's a large number of possibilities here, and it might be difficult to sort of see the whole search space at once. It's not easy to see that the first best move is the move where you go from tower 1 to tower 3. And of course, this gets much worse if you think about bigger problems. So, for the sake of time, we won't do this in class. But of course, computers can solve these things pretty well. So here's a little computer algorithm that goes at work and solves this gradually over time. So there's a very mechanical procedure that you can use to solve this, this problem. That's almost done. Oh, it's actually taking longer than I thought. All right, now it has the big one on there. Well, you get the idea. All right, we'll wait. All right, 255 moves. Can you do that? Well, maybe. Okay. The initial state and the goal state, those are both states within this large space. So when psychologists first started to think about problem solving and the psychology of problem solving, they thought, okay, well, problem solving is essentially a search problem. You have the space of all possibilities, you know where you are currently, you know where you have to end up, and basically you have to find the shortest path in this search space, which happens to be this path over here that takes you in 7 moves from the initial state to the goal state. And there are various other paths that lead you to the goal state as well, but those are not the shortest paths. So maybe from that viewpoint, everything is just, everything involving problem solving is just searching through this space. Now, this can get hard once you make, once you increase the dimensionality of the problem. So with 3 disks, there are only 27 possible states. You can still sort of manage to think about, all the possible configurations. But with 4 disks, you already have 3 to the power 4 as 81 combinations. And you can see that as you increase the number of disks, there's this sort of combinatorial explosion, an exponential rise in the number of states. Now, for some problems, like you probably know Connect 4 or 4 in a row, right? The problem where you have to line up these colored disks in 4 in a row. That problem has been solved. There are 2 trillion ways where you can potentially line up 4 disks in a row. And that search space is now well understood. You can actually enumerate all the possible ways in which you can win or lose. And people have shown that with Connect 4, if you start and you place the first disk in the center row, and if you play the right strategy, you cannot lose. And in fact, your best opponent will lose, guaranteed to lose within 41 moves or so. But there are other problems, like the problem of chess. You can't possibly enumerate all the states anymore. In chess, there are 10 to the power 43 possible combinations. So that's a 1 with 43 zeros behind it. And there's no way in which you can use a brute force technique to find a solution. So if the search space is very large, and most interesting problems have these very large search spaces, like the game of Go and checkers, chess. Computers can't navigate this space. People certainly can't navigate this space. So you need to use heuristics. And heuristics, as we talked about last time, they are procedures that are not guaranteed to work, but that work pretty well under many circumstances. So one strategy is trial and error. We'll discuss the trial and error, hill climbing, and means end analysis. So 3 sort of very general ways to deal with well-defined problems. So first, trial and error. We've actually already seen this in the chapter on learning. So the research by Thorndike suggested that many animals solve problems by trial and error. So he had these puzzle boxes for cats, where cats had to find a way to escape this box by trying a whole bunch of moves. And Thorndike found that at some point through a seemingly random move, like pulling on a string, the cat figures out how to escape this box. And cats, they are getting better over time in solving these problems. But this is a very gradual process of learning. So gradually the right response gets reinforced, but there's a lot of error involved. There's a lot of trial and error. Just a lot of random moves that are tried to see if something works. Now, it's important that trial and error it's important to realize that trial and error is a very powerful strategy. If you get stuck in some problem, doing something random, that might not be very creative, but it might be a very smart thing to do. Sometimes the only way to solve a problem is trying something random. Now, a little bit more informed of a strategy is hill climbing. So in hill climbing, you have a sense of how far you are away from the goal. So if you have a way to measure the distance between the goal state and your current state, then you can apply hill climbing strategy. Now this illustration might be a little misleading because here you literally are trying to climb a hill, but this is just used as an analogy for the more abstract ways of applying a hill climbing strategy. So suppose you have some hills in front of you and you're blindfolded and you can only feel sort of the ground around you and you can feel the gradient, so to speak. And you have to find the largest hill in your neighborhood. Well, a hill climbing strategy would be to find a step to take that leads you sort of in the sort of highest or the steepest gradient, right? So you find the strategy, the local step, that will reduce the distance to the goal as much as possible. But importantly, in a hill climbing strategy, you blindfold it here in this analogy, so you don't have this global overview of the whole problem space. You can only see locally around you. Now, if you would start over here and apply this hill climbing strategy, it's easy to see you would end up at the goal, right? You would end up at the highest peak. But one problem with hill climbing is that your starting point matters. If you happen to start at this position in the landscape, you would climb up this local hill, which is a local maximum but not the global maximum. And that's the general problem of hill climbing. Hill climbing, you are guaranteed to improve your situation over time, but it's definitely not guaranteed that you reach the best solution over time. You might get stuck in some suboptimal solution. So here's another illustration of where hill climbing might go wrong. Suppose you have this rooster, and the rooster has a sense of smell of food. The food happens to be behind a fence, and let's say that the smell of food can sort of go through the fence. And that the numbers here indicate sort of how strong the smell of food is. So a hill climbing strategy would be basically following the smell gradient. So if you start over here, a hill climbing rooster would take that one step that increases the food smell the most. It would go from 1 to 2, from 2 to 3, and now would get stuck over here. So this is the local maximum, because any move from here would actually lead to a worse current solution. And so here, a hill climbing strategy by itself is not sufficient. You have to do something else. That something else could be just trying something random, like a few random steps that happen to get you around the fence, or maybe have some kind of planning strategy and realize that going around the fence might be a good idea. All right, then the final general strategy for solving well-defined problems is means end analysis. So means end analysis is a bit more clever because you can not only execute moves like you do in a hill climbing strategy, but you can also plan for making moves. You can make a distinction between doing something versus thinking about moves that would enable you to execute other moves. So as an example, if you are a hill climber and you apply hill climbing strategy to the Tower of Hanoi problem, you could say, well, I try to get as many discs in the right position on the third tower. If I get 1 in the right position, that's better than 0. If I get 2, that's better than 1. But there is no planning involved there. But at some point, if you have an insight that really what you ought to do is free up this large disk, because that would get you sort of get you going in the right way, then you're applying a means end analysis. So in a means end analysis, you think about ways in which what's different between what I have to accomplish and where am I now? And can I decrease this distance to the goal by either executing a move or maybe creating a new problem, a new sub-goal, that if I accomplish that, then I get closer to reaching my ultimate goal. So in the Tower of Hanoi problem, you have to realize, okay, I have to reach the sub-goal of freeing up this large disk. Then you go executing that sub-goal, and then during that problem-solving process, you have to realize that you have to free up this third peg. And then you have to realize, okay, at some point, I can move this large disk onto the third peg. So you have this whole sequence of sub-goals that you set and trying to work on those sub-goals before you can even execute any real moves. Here's maybe a simpler example. If you want to paint your house, that's your ultimate goal. You might have set a sequence of sub-goals, like you need to apply paint, I need to paint and brush, I need to go to the hardware store. And you haven't done anything yet, you just set a bunch of sub-goals. And then finally you can go to the hardware store, you got paint and brush, you apply paint and you painted a house. So according to a means and analysis, you are constantly working on the last sub-goal, the last subroutine that you placed on a so-called stack. And it's only the last one that you can work on before you can work on any other sub-goal. There's this hierarchical structure in problem solving. Okay, so all this work on the well-defined problems has led to interesting insights on the reasons maybe why people can get stuck in problem solving. It's usually because the problem spaces are too large. It's hard to sort of navigate these spaces. Sometimes heuristics can fail. But the more interesting psychology is with ill-defined problems. So Gestalt psychologists at the early 20th century, they argued that for many problems, you don't quite know how to even approach the problem to begin with. You have to see the problem differently in order to solve it. Find some kind of representation to work with. So here's an example of what I think is a tough problem. And there are different ways to solve this problem. And some people would argue you have to really rethink the whole structure of this problem. So suppose you are starting this square marked by the circle, and you have to navigate by drawing a bunch of lines. You can't pick up your pencil as you go. You can't pass through a square more than once. You can't go diagonally. You can't leave the checkerboard either. Now, the question is, by navigating in some path, some wiggle path along this checkerboard, can you actually visit all squares if you start on this particular white square? And how are you solving this problem? So do you think this is possible or impossible? If it's possible, you have a path, right? But is that a valid path? You know how to do it? Really? There's a valid path?
Yes. So you go down all the way.
Let me
Go all the way. And then go across all the way. Yes. Then go only one square up. And then go as far as you can to the left.
So
Then go until no. One square higher. Yeah, right there. And then go over one. Then go down one. Go across all the way. Go up one.
yeah. Well, so there's so many ways to try it out, right? The solution is this is impossible. Now, and it's very difficult to see it by just thinking about this spatially. That's the point of this puzzle. You should not think about this spatially. You should think about this abstractly, more like a mathematician would think about this problem. Now, I'll tell you what the solution is. You don't know. You need to know why the solution works. That's not the point of the class, right? But I want to tell you anyway. There are 25 squares, right? There are 13 black squares and 12 white squares. What's the last square that you need to hit? Is that a black square or a white square? So you need to hit a black square, because otherwise you can't get all 13 black squares. The move before the black square, is that a white square or a black square? That's a white square, right? So the time that you hit the 13th black square, the last black square, you must have used up 13 white squares as well. But there are no 13 white squares, there are only 12 white squares. So it's impossible, and then you can prove that anytime you start in a white square it's impossible, whenever you start in a black square it's possible. Well, so basically thinking about this spatially, it was not very helpful. Thinking about this more in terms of, abstract mathematical properties of this game is more helpful. Here's another sort of famous problem. Maybe if you advance the slides you've already seen the solution. But for those of you who have not seen this yet, if you have these 6 sticks of equal length, how do you make 4 equilateral triangles? So equilateral triangle is a triangle with 4 equal or 3 equal sides, right? Equal length. Well, to save time, this is not a solution. It looks like you have 4. You have definitely 4 triangles, but they're not equal length sides. And some of you will stumble on this solution. You have to think 3-dimensionally, right? I think this is called a tetrahedron. Not sure about the official name. But you might be fooled into believing that you might even have these sticks, like matchsticks, laying on a table in front of you, and you start futzing around, and you are sort of thinking, you have this mental set, if you will, of thinking in a 2-dimensional plane. But you have to break out of this. Nobody said that you have to come up with a 2-dimensional configuration, right? 3D is just fine. So it's another example where you have to represent the problem in a different way. Here's another classic one from 1931 that stumps a lot of the subjects in this experiment. Suppose you have to paint a room, and you have these cords hanging from the ceiling, and for reasons I don't quite understand, you have to tie these cords together, because I guess that's what you do when you paint a room. And you can hold one of these cords, but then you can't reach the other cords, right? Your arms are not long enough. And you really need to tie them together for reasons I don't understand. And you see that there's some other things, in the room. So how would you solve this problem? For some of the creative minds among you.
Would you tie the paintbrush to the other end of one of the strings and you use momentum?
That's right. That's right. That's one of the solutions. Exactly right. Now, why do you think this might be hard for some people?
They don't think out of the box.
Yeah, what does that mean here, out of the box thinking?
They try to do it themselves, without using the other objects, and they're like, oh, I can do this. This is easy.
Yes. Yeah. So Meyer suggested that one reason why people get stuck with this particular problem is that they don't think of a paintbrush in this new way, right? You have to let go of some of your associations, right? You have to let go of thinking about the functions of certain objects, the idea that a paintbrush is only useful for painting, in order to solve this problem. And so Meyer suggested, well, sometimes the reason why we get stuck is because of functional fixedness. If we have to solve problems involving sort of physical setups, not so much abstract problems, objects that are used for one function, they could be used for other functions. And if you don't think flexibly, you're stuck with this functional fixedness. A more general term is mental set. So this is going to be applied more widely. If you have solved a problem or approached the situation in one particular way in the past, and that has worked, you probably will use that same strategy, that same mental set again in the future. If something worked before, let's do it again. And in some situations, you can do better, right? You have to break out of this mental set because there's another solution that's actually much better. For example, I've been driving to a particular location the same way for years, and then I finally did a Google search and found out that there's a much better way to drive, right? And I thought this was the shortest distance over all these years. Now here's another problem. Maybe we can solve this as a class. So here's the setup. Assume you have a steel pipe, this pipe, that's firmly embedded in a concrete floor in a bare room as shown below. The inside diameter is slightly larger than the diameter of a ping pong ball. So this ping pong ball fits in this pipe and is stuck at the bottom. And you are in a group of 6 people in a room, and you have these objects available to you. Now, how can you get this ball out of this steel tube and realize that the steel tube is 4 feet long, so you can't just stick your hand in it, and there's no other person who has hands small enough or long enough to just grasp the ball. So how can you solve it? Well, you have some clothesline available, you have carpenter's hammer, a chisel, a box of Wheaties, a file, a wire coat hanger, a monkey wrench, and a light bulb. So this is a problem-solving exercise. There's no one solution, there are probably multiple solutions. Can anybody think of a reasonable solution to use here? To get that ball out of the steel tube without breaking anything? Which objects could be useful? Yes?
My first thought kind of goes to the wire coat hanger. If you undo it and like kind of stretch it out and make maybe like at the end kind of like something big enough to get between it, but kind of almost pull it out.
Like a snare of some kind, yeah. That's right. And some people, they think, oh, let's take the light bulb apart, use the filament, and make a snare out of that. That's a similar idea, right? Does anybody have another idea? Can some of you think really outside the box?
Like crush up the Wheaties and then just put them in the tube and use the hammer for vibration so all the Wheaties are at the bottom and push the ball up.
That's good. That's good. Yeah. Some people say chew the Wheaties, so it develops a paste, right? And it sticks. That's another way of thinking.
Is the concrete floor like broken, or is it concrete floor, or because it looks like a piece of concrete?
Oh, yeah, no, it's just a diagram, a section of the floor. It's one big floor. Yeah, you can't lift it up. Yeah. Well, so occasionally there's a person who pipes up with a very unconventional solution that I like a lot. You have 6 people, right? 6 of your friends. What could you do? Well, how about peeing in that steel tube until the ball starts to float up? It's not the solution, it's a solution, and it works, right? That's clearly thinking outside the box. I like that solution. Okay. So Gestalt psychologists who studied all these ill-defined problems, they suggested that an important concept is the concept of insight. Sometimes when solving these problems, you see the problem differently, and you have this experience of an aha moment, which might be accompanied with just the moment of solving a problem. It might just be that you think about it in a different way. But how do we know when something requires insight or when insight is involved versus some other type of problem-solving process? Well, one of these Gestalt psychologists, Kohler, during the Second World War, he was stuck on an island with a group of chimpanzees. So he did some interesting experiments and took some pictures. So he tracked one of these chimpanzees that was particularly clever, this female chimp, and he gave this problem where he was suspending a bunch of bananas from the ceiling, and this chimp was at first sort of walking around a little frustrated, trying to reach this set of bananas. And then according to Kohler, this chimp had a moment of insight just by observing this chimp doing the following sequence of moves, where all of a sudden the chimp was putting these crates stacking on top of each other, and the chimp solved this problem. Then Kohler claimed that there was a moment of insight before solving the problem, that this was not solved through some kind of trial and error process. But it's very difficult to understand, when is something an insight moment, when is something trial and error? It's very difficult to tell. It's very subjective. So let's look at this clip. It's a very similar setup. The pigeon and the banana, I guess. I guess that's a banana at the top. Maybe it's something else. But the question, is what's going on here? Is this an insight problem-solving process or trial and error? Yeah, so I got there. Very good. So it's seductive to say that there was a moment of insight when the bird started sort of pecking or moving the little block. But it's quite hard to tell. So how can we really distinguish between problems that are solved through some insight process versus some other, more standard type of process? So Janet Metcalf did some really interesting research where she showed the differences between insight problem solving and more rote problem solving. So she used two different kinds of problems. One were problems that she thought were non-insight problems, like factor this equation here. So we have to apply some algebra. And some problems that she thought would require insight, like this one. A prisoner was attempting escape from a tower. He found in his cell a rope which was half long enough to permit him to reach the ground safely. He divided the rope in half and tied the two parts together and escaped. How could he have done that? How is that possible? What's the solution here? How can you divide a rope in half, tie it together, and then all of a sudden... Yeah, so the solution here is not to think about dividing in terms of cutting a rope, but unraveling the strands of a rope and then tying the strands together. Right? So you have to use a little bit of creative insight there. And one of the things that Metcalf did was to ask right after the presentation of the problem, like how much do you feel you know the solution of this problem? And subjects were giving a rating of the feeling of knowing. And one interesting result was that for these non-insight problems, the feeling of knowing could very well predict the eventual success. So people looked at these, mathematical sort of equations, and they thought, okay, I think I can solve this, or I cannot solve it, and that was indeed right. But when they were thinking about, can I solve this prisoner escape problem, their feeling of knowing was not predictive at all. Another thing that she did was to ask for these warmth ratings, like how close subjects thought they were to solve the problem, over time as they were solving the problem. So the ratings were from 1 is cold, I'm nowhere close to the solution, to 7 is hot, problem is virtually solved. Now these are the results that she obtained. Now on the left column, we see these warmth ratings for insight problems, right? The prisoner escape problem. On the right-hand side, we see it for these, what she would claim are non-insight problems, the algebra problems. Now each panel shows a histogram of counts, basically counting how many times was a certain rating given. Like how many times there was a rating of 1 versus 2 versus 7 given, right? So 7 is hot, 1 is cold, and nowhere close. And then the interesting way in which she organized the findings was by going back into time. So the top row shows you what the ratings are when the problem is basically solved. And not surprisingly, people, when they are solving it or almost close to solving it or at the moment of solving it, they give a rating of 7, everybody. Now this row shows you what the ratings are 15 seconds before solving, and then this one 30 seconds before solving, up to 1 minute before solving. Now what is the difference that you see here between the left hand and the right hand side? What is the difference between these insight problems and these non-insight problems?
With the insight problems, it's almost, it looks more like there's an instant notice, or because they're, well, they do kind of gradually get closer, for the most part, all of them are still at 1, and all of a sudden they're at 7.
Yes, exactly. So here you can see that this distribution or this histogram for insight problems is basically the same. There's a bunch of people that say 1 and fewer people say 2 or 3 or 4, and it stays the same 1 minute, 45 seconds, 30 seconds, 15 seconds before solving, and all of a sudden this whole distribution moves over to the right. But for algebra problems, you see that this whole distribution gradually moves over. People are getting a sense of, oh, I'm getting closer and closer and closer, right? So you see this peak over here is gradually moving to the right-hand side. So this is how Metcalfe sort of distinguished between problems that require insight versus no insight. This sudden sort of change in feeling of knowing or feeling of closeness to solving. Does that make sense, these results? Okay, so final topic, expertise. We all know, we are acutely aware of individual differences. Some people are just much better at some tasks than others. Some people are really, really good, and everyone wants to know what makes certain people so good at some tasks. Whether it's in a knowledge domain or, let's say, in some physical domain like sports. So how can you become an expert? What does it take? Well, in knowledge domains, one of the things that you need is extensive experience. You need to have a lot of background knowledge that you develop over many years of training. And this training will allow you to see patterns that other people might not see at all. So one example is radiologists. So if you go to the radiologist with a broken leg or something, you probably will recognize a broken leg, right? That sort of pops up very nicely. But other things don't pop up nicely at all in these x-rays. In fact, you might be looking at something that's abnormal and you think it's perfectly normal. So one of these two x-rays is quite bad. It's a bad condition. You need to get medical treatment soon. And one of these is perfectly normal. And can you tell which one is which? Well, the answer is written in reverse. You probably figured it out. So this one is the abnormal X-ray. And probably nobody of us is an expert, and I'm certainly not an expert. But somebody told me that this shadow over here is quite bad. That could indicate a collapsed lung. right? And you need to look over here to find it. And everybody looks at other features. But radiologists, they developed this rich database of patterns, normal, abnormal. They see this whole X-ray in a three-dimensional way. They just see a lot more things and see it very quickly. There's a lot of chess studies that investigated the differences between the very good chess players versus the novice chess players. And there were some surprising differences. You would think that a really, really good chess player can think about an enormous number of moves and can think very deeply. So can think a large number of moves ahead. But what this researcher, de Groot, found was that the very best chess players, they only consider about 30 moves at a time. That's a pretty small number. You can also think about 30 moves at a time. And they thought about 6 moves ahead. That's actually not that impressive. But of course, the 30 moves that they are thinking about, they're really good moves, right? And so they're weeding out a lot of moves that are quite terrible. And how can they do this? Well, master chess players, they have this extensive experience. They build up this whole database of like 50,000 patterns by some estimate of configurations where you know, okay, if I do this, then this leads to some advantage. And this takes years and years of training. So skip this, we already talked about this. And so this has, there's some interesting findings where the amount of training that you need in a specific knowledge domain or sports domain is quite high. So you need to train very specifically for that particular game, like chess, or for that particular sport in order to excel in that sport. And we sometimes think that skills can transfer to other similar domains. That a chess player can play a good game of checkers. And that's probably true, but they can't play at the world level, let's say. A master chess player can be a master sort of checkers player. Even domains like baseball and softball, which seem very similar and rely on similar visual skills, they're quite different. And there's this interesting anecdote that's reported in this book, The Sports Gene, which I highly recommend reading, where there was a bet of some kind, where some Major League Baseball players, they thought that softball players, the pitch of a softball player, that they could easily hit that. Because the softball is going at a lower speed, a softball is pitched at like 60 miles an hour, whereas baseball players, they regularly deal with these 95 miles an hour pitches. So this girl, Jenny Finch, she's the top pitcher in softball. She pitched against 2 big Major League Baseball players. I think Barry Bonds was one of them. And she struck them out decisively. And Barry Bonds and Albert Pujols, I think, they were quite surprised. Like, why can I not hit this softball pitch, which is closer to where I am and is going at a lower speed? And it turns out they have all the wrong experience. They're dealing with the wrong visual angles of the ball coming in. And so all of these years of experience, which helped them to become so good in baseball, was working against them in this game of softball. So training needs to be very specific to lead to expertise. And by the way, here's you might want to watch in your own time this funny video clip where this Major League Baseball player is struck out by Jenny Finch. So there's a lot of research that tries to understand, okay, what are the factors that leads to expertise? Is it talent, IQ, practice, genetic factors? As I said before, most experts, they are experts in their own domain. The skill that one develops often does not transfer very well to other domains. And the one controversial finding in this area is the so-called 10-year rule. So all this research that shows that you need to spend a massive amount of time training for something very specific has suggested this rule, the 10-year rule, that if you are engaged in deliberate practice for 10 years, essentially like 3 hours a day, and then 10 to 20,000 hours total, you can develop some international level of expertise. And the psychologist who proposed this, Anders Ericsson, he said it's not just passively doing the sport or the game, like a game of chess. You need to be fully engaged in the practice. You need to monitor your own performance, think very carefully about, if things go wrong, how can I improve? But then the premise is, as long as you put in all this amount of time, you will become an expert. Now here's one piece of evidence that he used to suggest this sort of 10-year rule. So they studied some musicians over time, and they were tracking the amount of time that musicians, like violinists, practice in their craft. And they made a distinction between the very best violin players, the ones that can get a job, let's say, in an orchestra, versus the good players, and then sadly, teachers. People that, the students that said, well, I'll become a teacher instead of pursuing a career. And as you can see here, this plot shows the cumulative amount of practice over time. So by the time, by 20 years of age, the very best violin players, they have accumulated about 10,000 hours of practice, right? And that amounts to like 3 hours a day for 10 years. Whereas teachers, they put in less than half that amount of time. So Erickson showed this association between amount of practice and performance. But the big problem that he did not look into, is the cause-effect relationship. Is the reason that somebody becomes good, is it because they practice a lot? Or is the reason that they become so good is because they want to practice, because they realize they're good, and that's why they practice so much? So we don't know cause-effect here. We don't know if increasing the amount of practice would actually make you better. Maybe what really matters is just intrinsic motivation. Do you really want to be engaged in this activity to begin with? So there's a lot of controversy around this rule. There's this book, I think it's Malcolm Gladwell's book, called Outliers, which is, I think, a terrible book, but a lot of people read it because he naively cites some of Ericksons' research and then comes up with these loose recommendations like you should just practice more and that will make you perfect. There's a lot of reasons why one can think of that practice is not the only important factor, right? You should really enjoy the activity to begin with. You should be intrinsically motivated. You should have the right sort of genetic factors that will enable you to reach that international level of performance. Yeah, so I'll leave it at that, and we'll talk some more on Thursday.